Okay. Okay, that's good. Then noise time is yours. So please go ahead. Yeah.
Awesome. All right. Thanks for having me. Feel free to interrupt me anytime if there were any questions. I would like to have some discussion and hear from you too, because in the beginning, I'll show a couple of ICCV papers that we had, but part of the towards the middle and end, I have some open questions. So I would like to hear everyone. So it would be great if we can have a discussion as well. Okay, so thanks for having me. I'm Amir. So the first and the biggest piece of work that I want to talk about today is making steerable vision data sets, especially that this is in the context of, there's a multitask learning workshop, and I think these data set pipelines that I've been working on are pretty useful for multitask learning. I think one of the things that multitask learning research in general needs the most is bigger data sets, more controlled data sets, something that let us analyze different aspects of multitask learning in terms of architecture and so on. So I still remember before we started working on this pipeline, which originated from the taskonomy basically, and Gibson, it was really hard to actually find good data that would allow concrete research on multitask learning. We would have to mix like MNIST and CFAR and call it two different tasks, or we would have to like break up CFAR classes into say 50 classes, pairs of classes, and call it different tasks. So it was really hard. And when we started with taskonomy, the first thing that we tried to do was to have one image, but instead of mixing different data sets, have one data set, but that has multiple annotations. So each image was annotated with 20-ish different tasks. And that was the beginning. But since then, we have realized that there are more things are needed, and it wasn't nearly enough to run that pipeline once. And it gave rise to this piece of work that we presented in ICCV this past week. This is a great work done by Aina, Sasha, and Roman, along with Jitendra and myself. Everything that I'm going to talk about, code and data and a bunch of demos and interactive stuff are on this website, omnidata.vision. So regardless of the talk that I'm going to give, I really recommend, if you're interested in this area, just take a look at this. It'll be useful. Okay, so the main idea is the following. Most of the vision data sets that we have are basically recorded once. There's a photographer that visits a scene and takes a picture, and that picture becomes the depiction of the scene. And we can't change it after that, just because the way everything works, the way that you don't have access to the scene, and the cameras basically record one snapshot and so on. There are complex ones such as light field and so on that gives you some level of variability and control, but still you can't do anything like moving around in the scene or making certain changes like lighting change and so on. So basically what we end up with in the existing vision data sets is that a set of images are recorded once, and afterwards we add some annotations on top of them, and then learning and analysis and evaluation, everything starts from there. And now I think the problem is even a little bit more than that, because these images are collected in an uncontrolled way as well, meaning that mostly they're coming from the internet. And we all know that we take, well, from Flickr, Panoramio, and so on and so forth. So, and we all know that like these are taken by humans, and we humans, why do we take pictures of things? Because there's something interesting in them for us. We don't take pictures for the sake of pictures. So in a way, those pictures that we collect and we put that in the internet and become our vision data sets, they are very different from what our robots and vision systems will ultimately see in the real world, because they're going to just see this mundane, real world, boring scenes that nobody takes picture of. So they become effectively out of distribution, ironically, if we continue collecting data sets purely based on human user uploaded images and the internet. So, okay, so here's the idea, like, can we do something better than that? And the fact that these data sets that we have heavy biases are known. Many papers have done this analysis. For instance, is the distribution of viewpoint of sofas, multiple objects, but I'm highlighting the sofa here, that you can see that most of the sofas are depicted from the frontal viewpoint. There are very few pictures of a sofa from a side viewpoint. This basically means if you train an annotator, train a neural network on this data set, it's not going to be able to handle a sofa when it's depicted from the side, from sideways, which is obviously less than sufficient. And like I said, multiple papers have done this analysis. There's this very nice paper by, I think, by Antonio and I think Aliusha from a decade ago that on the right, you can see, do you see my cursor or no? Can someone give me some feedback if you can see my cursor?
Yeah, we see
Oh, yes, we do see your cursor.
Yes.
Okay, cool. So yeah, this paper from Antonio from a decade ago. So they have this nice data set guessing game, is that by just looking at the images, you can tell from which data set they're coming from, because they are basically quite biased. That's a representation of the bias that we have. Okay, so, and this is quite a critical problem. Like we, for instance, collected this taxonomy data that was, in our opinion, pretty controlled, because we were not even sending a photographer to the scene. We had the it was collected using 3D scanners, such as like Matterport and Cardo, and those like popular scans at the time. And then we thought, so they were collecting panoramas, and we were collecting the images out of the panorama. We were sampling them into rectilinear images, and that was becoming our data set. So we thought it was more controlled and less biased because we were specifying the camera parameters. But still, like when we would train a neural network on it, it would poorly handle the scenes as soon as the query image goes out of, even to the slightest, goes out of the camera specifications that we had covered in the data set. So it made it clear that we have to do more on this front. So the idea is that, okay, let's say if we can close the loop with dataset generation and make these datasets created in a more closed loop manner with respect to the desired properties of the user. So let's say if you can have our dataset creation pipeline. First of all, this is a pipeline that creates dataset. So the input is not like a set of pre-recorded images that photographer took and we are only annotating them. The input is a 3D scan. I'll explain it in more details. But using that, let's say if you can expose a set of parameters that the user can play around and press a button and a dataset is rendered, and that becomes the basis to learning. So for example, field of view. Field of view was a critical parameter. Field of view was basically my nightmare for a few years. Every time I was looking at, we had these live demos up on the website. And every time I wanted to upload a picture and demo that it works, it was my nightmare whether it's too wide or too narrow, because I knew that if it goes out of, I think it was 60 to 90 or 40 to 90, something along those lines. It was quite a wide range, but I knew that it goes from like, from 40, it goes to 35, it's not going to handle it anymore. Or it goes just 5 degrees higher, it's not going to handle it anymore, it's going to completely crash. So even though it seems pretty simple, it was still a quite big problem in terms of the robustness of results. So let's say we can control the field of view, which seems like a pretty obvious thing, but if we can control the generation of the data in this sense, so we could relax and not worry about the generalization, because evidently the neural networks are not handling it internally. They do not generalize to these camera specification parameters, intrinsic and extrinsics, as well as like the scene parameters. Okay, so here what you're seeing is that low, medium, and high, these are different field of views that we have generated from one scene. And you can see that the content of the image changes quite a bit. And that's precisely why the neural networks don't generalize. Apparently, evidently their inductive biases was not enough for generalization in that case. And similarly, there's more you can do, for instance, object centricness versus scene centric. Like depending on how close you are to the scene content when you're generating the image, you can get something like a really large field of view, something like that, or you can get a close up like these. And again, these were like pretty obvious in terms of failure modes in the neural networks that we were training on. And we benchmarked a whole bunch of them. So it wasn't specific to our pipeline and so Okay, so let's say if we can make a steerable data set, and a steerable, it basically precisely means that you give the user more control over the data generation pipeline. And that's precisely what Omnidata did. We have exposed a set of parameters that the user can specify and then render the data set. I'll explain it a little bit more detail, but let's just see what we got out of it as a teaser. So first, like, we ran this with a set of starter data sets. We got basically a whole bunch of 3D scans from different existing 3D scans. We didn't collect new ones, but whatever was available. And we rendered about 14 million images out of it, and we trained some neural networks on it. And they worked remarkably well. They work better. I mean, they're state of the art for the tasks that we trained them on. So I'll show more details about it. Like, those are like depth and normals and so on and so forth. I'll show more details. But just right now, just this pipeline was enough for us to get a state of the art. So hopefully this will let people, like I said, close the loop in terms of data generation and understand the aspects of data that leads to better generalization and so on. So you can think of it as a data set design guide, because now you have some parameter to control. We don't have the guide right now, but now this is a platform to start creating a guide out of it. And we can do kind of some controlled experiments like match pair analysis, that let's say if you have two data sets, we have ImageNet and we have NYU, if we train a neural network on it, these are pre-trained weights, and we go to a third task now. Everybody knows that if you pre-train on ImageNet, fine-tune on ImageNet, it's better than fine-tuning on NYU. But what exactly is the reason? We don't know the exact reason. It's just a common empirical observation that ImageNet does better. But if we have a data set that has control parameters, we can start doing match pair analysis that answers these more basic questions that right now empirically we are capitalizing on, but we don't have an understanding around them. And as their 3D scanners are becoming more ubiquitous. Now iPhones and iPads have even a LiDAR integrated in them. So I expect to have more 3D scans, maybe VR again. We have been saying that for several years, but maybe VR, AR applications will be another avenue and incentive for people to create more 3D data. And this, as it becomes more popular, hopefully we'll have more and more 3D scans and we can create more and more data sets. So this is basically a pipeline to turn our 3D scans into image data sets. Okay, so let's just very quickly look at how it works. So the input has to be a form of 3D and a form of RGB information. It could be aligned images with the underlying mesh, such as what building parser or 2D 3ds or Gibson or Taskonomy and so on did. The texture, the mesh wasn't texture in that case. We had a mesh and we had like aligned RGB images, or it could be textured mesh. There are plenty of those data sets, or it could be point clouds. So one of these forms of like common forms of 3D, and the pipe goes through the pipeline renders this into a bunch of images sampled from around this space and a bunch of annotations from these. And these annotations are either based on geometric processing of the mesh or propagating the semantic information that came on the mesh. So to give you a quick idea about how this framework actually works, first, like this is the input mesh. We do a bunch of sampling to create fine camera parameters. Either these are like sampled with some pause on disk, for instance, sampling, or users can specify the exact camera parameters that they want to generate. And then, oops, I'm going backwards, sorry. All right, and the second point is that we sample points of interest. These are points on the scene that we want them to be depicted. We basically use them as anchor points. For instance, you have 3 camera viewpoints and you have 1 point of interest, and all these camera viewpoints are now fixating on this point. That point, that physical point, is now in the optical center of those 3 cameras. Because everything is under control, we can do this kind of things. So that's what the point of interest, basically sampling over the scene content. And okay, so you can do, like, you can use your imagination now, see how much we can do with this. We can create wide baseline pairs. We can create like narrow baseline pairs. You can, for instance, compare these 2 viewpoints that are here They show the red cross in the optical center of both, but they are from widely different viewpoints, a little less than 180 degrees, whereas these two have a closer viewpoint. Okay, and we can also do it as a video, obviously. We can sample various viewpoints in the scene and just smoothly render a trajectory between them. So you can think of it as, like, let's say, training your optical flow algorithm on this, or viewpoint estimation. Okay, and this was about how to generate the images. We generate a whole bunch of cues or outputs on top of this. Those were input, and now this is output. Output are these standard things that you're already familiar from. If you're familiar with taskonomy and Gibson dataset and so on, these are like surface normals and depth and curvature. These are the common ones, or segmentation. So if these meshes are coming from segmentation, which most of them do, those that we work with, we can of course project those back onto the pixels and have like a semantic annotation too. So this is basically what it looks like for a subset of those tasks. We have the same tasks that we had in taskonomy 20-ish, but this is showing a subset of them. So I can see that there's like, now we have a RGB set of frames rendered, and aligned with that we have the semantics and surface normals, 30 key points, occlusion edges, and so on and so forth. Okay, so we did this to use this pipeline to create a starter data set that has like 14 million images, roughly about 2,000 spaces. So what we included, this is again a subset like replica, clever, hypersim, Google Scan Objects plus replica. Google Scan Objects was great because it would give us object, like close-up of the objects, but it doesn't come with a scene, so we had to integrate them in some scene. So we dropped them with some heuristics and physics-based constraints in replica scenes, and we rendered basically GSO in replica, Google Scan Objects. Obviously taskonomy and blended MDG. And also recently we integrated the new Matterport dataset, the 1,000 spaces. And these are what you're seeing in the columns are the outputs. These are images, and these are basically different tasks: semantics, normal, Z-buffer depth, Euclidean depth, and so on and so forth. And some of these datasets actually already came with some of these domains. For instance, hypersim came with semantics, normal, and depth, but not the rest of them. So the red boundaries that you see specify the tasks that only were created through Omnidata pipeline, and they were missing in the original data set. So it has made all these domains kind of uniform in terms of the outputs. Okay, and obviously it's a pipeline. This was a starter data set. This is a pipeline, so we can just take it, clone it, and run it for your desired data set. It can be done, like I said, the requirements of it are pretty broad, so you can use it for any domain that you have, as long as you have some form of 3D and aligned RGB. Okay, so just give you a quick idea about the results. Like I said, we trained it on, we created a starter kit, and we trained it some DPT models on top of it. And Midas has been a pretty good depth model. Some of you might have worked with it already. And these are the results compared to Midas. And this is, by the way, exclusive of Midas like data. Midas itself was a superset of multiple data sets. We haven't, what the results that you're seeing that it says ours is actually not including that superset. We are now training a model that even includes that. Hopefully we'll get even better results, but even without it, you can see that the fine grain details are a lot more pronounced here, and generally depth is a lot more robust. And yeah, more examples of that here. You can see that, let's say, the face of the cat, a lot more like geometric details are coming out. This is probably best seen if you look at the surface normals that are extracted out of depth. You can see that, like for instance, for Midas, it comes out pretty like flat. It almost seems like it has decomposed the scene into a set of layered depth. Whereas like when you extract normals out of it from our method, you can see that the face of the cat is not more coming out like a poster. It has some shape information in it. And for reference, these are the results that we had last year in Crosstask Consistency, which I thought was pretty good. But on the left, we can see that again, just improving this data and controlling the camera parameters without all the fancy blah blah of cross-task consistency and so on. It already outperformed it. Again, we are now training a model including cross-task consistency constraints. Hopefully it squeezes out more juice, but it seemed like data won over method, and some more examples. So, I mean, just to give you a very quick example of the analysis that this could allow you to do. Let's say, for instance, would having these like mid-level cues, like geometric cues primarily, help a supposedly high-level task like semantic segmentation, like COCO? Yes or no? So now finally we have a data set and a pipeline that we can actually put this into a concrete test. And the answer was, at least based on the set of experiments that we ran in a important paper, that yes, having more mid-level Q domains substantially help with doing better semantic segmentation. So I have to say this is just a sample study. There's a lot more work to be done to get these results to be unquestioned. Okay, cool. Oh, one last thing that I wanted to say is that just also remember that these pipelines, I mean, this is not synthetic data in the sense that this is not based on some user or like artist designed CAD models and so on. These are actually real world 3D scans. So there's not going to be that much concern about domain gap with the world. There's going to be some concern with domain gap with the real world. Let's say if the rendering pipeline introduces some artifact, but we haven't really observed such a thing. So when you render an image, it comes out pretty good. And you saw it in the neural network training results too. But since everything is under control, at least in terms of geometry and camera viewpoints, we can do like new stuff, like for instance, new 3D data augmentation. So here you can see that we are changing basically a parameter akin to aperture of the camera. So it changes the focus from near focus to far focus. It gives you a shallow focus, first of all, and then you can move the focus across different parts of the scene. Okay, just to give you an idea. And so yeah, it's mandatory YouTube video that you have to see. There is a live demo on the website, so feel free, visit it and test, upload your images and see how it works for you. Okay, so, and there's also a Dataset Explorer, like everything that I said, yeah, there's a controllable parameters and so on and so forth, but you can go to this Dataset Explorer web page and start kind of playing with some of these controls and see how it changes the data that you receive. You can see that sometimes, if you go too narrow in some of these domains, which typically our vision data sets they're pretty narrow in terms of some of their camera specifics, you'll get pretty constrained images, which is the reason that we don't later generalize when we train on top of them. Okay, so this was the data about the steerable data set. I wanted to discuss some open questions that I don't have necessarily answer to right now, but I'm hoping that some of these would turn into projects in the near future, and ultimately maybe we can have answers, but like the questions on their own are pretty interesting. And we'll see how far we can discuss them. For some of them, we have some results. For otherwise, I'll be happy to also leave it at the question level. But let's just see. So first of all, okay, this is a multitask workshop. I have been working in this area with my team for quite a few years, but there's a lot more unknown that I would have anticipated. First of all, let's remember what is a task, like vision tasks. What does that even mean? Generally speaking, the commonly referred to definition is that these are useful abstractions from the world, like surface normals, depth, semantics, and so on. These are just useful things from the world. And where is the source of being useful? This is sometimes these tasks are defined based on some theories that we have. For instance, semantic segmentation is based on primarily the problem of grouping, and grouping is rooted in like Gestalt psychology. So some of these tasks are coming from such roots. Sometimes they're more into anatomical or neural cues from like real agents. For instance, it's believed that we have photoreceptors. I mean, by we, I mean generally any biological organism. Many of them have photoreceptors and neurons sensitive to motion and change. So you could think of it as a support for defining a change task, like optical flow and so on. But most of these tasks are based on intuition. We have to accept that many of these tasks do not have a concrete theory or explanation why they are useful and so on, which questions their usefulness and emphasizes the impact of understanding them better, because many of them might as well just not be as relevant as we think they are. So first of all, let's see, even if you get past that, fundamental existentialist questions, that we have to think about how we define, express, or parameterize a task computationally. So we should recognize that most of our definition of a task is data-driven right now, meaning that we get a data set, we annotate it. The way we express a task are these two annotations. The human belief that this is the association between this input and output. It doesn't have to be the only way. For instance, we can define it analytically. Some task, if you have a model of the problem, we can define it more analytically. Say this task is governed by this equation on this type of data, right? So that's more analytical definition rooted if you have a model of the problem. Or it can be relational. You can define some task A and then define some function A to B, and therefore you have this defined task B with respect to A. And this is something that, for instance, we did in Crosstask Consistency last year, which I think probably I don't have time to show you. But that was basically capitalizing on these relational properties of different tasks to create a multitask setup that is more robust. Dengzin, can you tell me, like, how many minutes from now should I end?
Yeah, it's still okay. I mean, you still have 10 minutes, I think. So you can actually
10 minutes. Okay.
Yeah.
Okay, cool.
Yeah.
I thought that was just about, okay, cool. 10 minutes is great. Awesome. Okay, and after that, so then sure, I can quickly show you some related results. And after that, we have to ask these questions: how we characterize a task. Like if I give you a task, what is it like? There are some important properties of a task that we need to know, and they have practical ramifications. For instance, learning speed. We have very few methods around like how we characterize a task other than a data-driven way. Like again, we have to recognize that most of the things that we call a task or based on intuition are defined in a data-driven way. So if one task is, let's say, computationally or information from the information theory perspective is inclusive in another task, we don't have a way of kind of getting that. Everything is pretty much data-driven and is mushed together in neural network training. So let me show you something in this relational stuff, and we'll come back to the rest of the discussion. So this was a paper that we published last year on Crosstask Consistency. I'm not going to get into details of it too much, but just to give you basically what relational mean, an exemplification of that is that, let's say today, if you want to get an image and extract, say, 5 different domains out of it, or 4 here, surface normal, reshading, depth, you can either train an individual neural network for each, like RGB to surface normal, RGB to depth, RGB to curvature, or you can train a multitask network, which typically means that there's a shared backbone and dedicated decoders for each of these tasks. The common issue is that these are not consistent with each other. So if you, for instance, zoom into these like little windows that I have shown on the screen, you can see that even though these are all geometric tasks, let's say surface normals and depth, the predictions are not consistent with each other, even though this was trained on one data set with the same exact images and the annotations supposedly were perfectly consistent with each other. Still, something goes missing when you train individual neural networks. So it means that these models do not get consistency to emerge naturally. It has to be explicitly constrained. So that's the problem. If you look at these like shape information here, for instance, the surface normals, depth has a completely different bump here. So the idea was that whether we can get these consistencies across different tasks to emerge organically in a learning framework. And if you think about it, and here's the actual results of the pipeline. So you can see, oops, sorry. Okay, it's going to transit, so I'm going to just show you over here. It's like now if you look at the details of 3D from any point across these different domains, you can see that they're more consistent with each other, meaning that, let's say, if there's a little like hollow part here, there's a little hollow part here, there's a little hollow part here, and so on and so forth. And if you think about it, why I'm talking about it here is that for being able to solve this problem, you have to understand the relationship between different tasks to be able to computationally enforce it. And that's basically this red edge here. This is precisely the depiction of an elementary formulation of our pipeline, that from X, instead of predicting X to go to Y and what go to Y2 independently, we actually add these constraints, the red part, as a form of, let me show you actually here. Yes, so X to Y1 and X to Y2, if you train it individually, you'll end up with no constraints enforced between these two. We introduced this little edge here that basically trains F and G with respect to each other subject to the constraint H, which means that you predict Y1 out of X, but then using the function H, you project it onto Y2. Also, you predict Y2 out of X using G, and you basically make sure that these two are the same thing. And that's precisely what the added constraint to the loss does. And if you do it, I'm gonna skip this part because I think we don't have time, and I'll show you the results here. Yeah, if you do that, like this is depiction of the consistency juice that you get out of it. So if you get this RGB image and you, let's say, extract 3D curvature or depth and shading and so on from it, and then project those onto surface normals, these are the results that you get. You can see that the surface normals quite wildly differ from each other, which makes sense because it means this, for instance, curvature had some errors that if you project it on the normal, it shows how the errors looked like from the perspective of normal, or depth had some error if you project it onto normal, how the errors would look like from normal. So since these different domains all have different error modes, therefore the depiction of those error modes in terms of normals would differ too. Here is the results that you get out of our consistency framework. You can see that the normals are a lot more similar to each other in constraint, which means that it kind of converged the error modes of all these different domains to be the same. Okay, so let me show you some results of it over a video quickly, which probably makes more sense. So now if you look at these, like this is like a YouTube video, if you pay attention to one pixel across these different domains, it's hard to find a point where these different predictors have suggested contradictory predictions for these images. And again, go to the website and run the live demo. This also consistency.epfl.ch. This one also has live demo. And in this ICCV, we also turned this into a more robust version of this cross-domain ensembles. The whole idea was that, let's say, if you look at these different paths that we had, these are basically an ensemble, right? You go from RGB to surface normals through depth, through curvature, through multiple things. So you can think of it as an ensemble already. And so we ran this as the idea of the ensemble is that you want to decorrelate different errors to get a finally better results. Now, that basically means these members of the ensemble that they have to be decorrelated. They should have different error modes. Basically, they have to be diverse. And most of the work in the community are in ensembles around like how to initiate these diversities to be present in the models. So different initializations, for instance, deep ensembles does that like through the virtue of like a stochasticity in initialization. We hope that these members of the ensemble end up being diverse, but that's not necessarily the case, and different hyperparameters and so on. So what we did was basically using these middle domains or these cues that I discussed earlier to enforce the members of the ensemble to be diverse from each other. For instance, if you receive this image that has been distorted and extract a set of middle domains from it, let's say 2D edges or a low pass filtered or grayscale or embossed filter, and you learn to predict, say, your target domain, in this case, surface normals, from these middle domains, you will get these set of different predictions. Okay, and if you can merge these two in some way into one final prediction, you would hope that you'll end up with a more robust final prediction, because these are different domains and they are impacted by different distortions differently. the error modes are not the same. So if we can do this merging in a robust way, which we do in a probabilistic framework in this paper, you'll end up with like better final results, which did happen. So I'm not going to get into details of it, but feel free to see the oral talk on the website. Okay, so that's about cross-domain ensembles. Oh, by the way, also I wanted to mention this 3D common corruptions because this is related to the 3D data augmentation that I mentioned earlier in Omnidata. So you're probably familiar with common corruptions. Common corruption, you know, you get an image. This is a great paper by Hendricks and Dietrich that you add a whole bunch of noise to the image, like a snow, zoom blur, Gaussian blur, and so on. That has been a way to benchmark the robustness of different methods. But these are all in 2D. These basically corruptions are astronomically unlikely to happen in the real world. So what we have done is to turn this into 3D common corruptions that we haven't released yet, but soon we will. So remember that the aperture change that I mentioned, you can think of it as a corruption, but it's a corruption that is consistent with the 3D properties of the scene. Or like defocus blur and motion blur. Motion blur does not impact all the content in the scene uniformly, right? It only impacts the content of the scene that is closer to you more versus the one that is fair. That's why if you take a picture of a scene when you're in your car, you will get motion blur of the content that is closer to you, and the mountains in the back are pretty sharp most of the time. So that's basically what common corruption does. We're going to release it soon, but for you to have an idea how we're going to actually continue working in that front. Okay, so I think I'm almost out of time. Let me show you one quick plot on the characterization of a task too. So what do we mean again by characterize that? If you give me some task, let's say in a data-driven way, we need to be able to understand some useful properties of this task. And by useful, again, there's like a lot of discussion, what is a useful property of a task to be known, but it's not debatable that learning speed is one of the aspects of it. So this is inspired by a paper on learning curves by Derek Cohen and his colleagues in ICML 2021. So basically what they have is that, let's say if you have a task, say surface normal estimation and so on, and you train a neural network using this X amount of data, let's say 100 images or 1,000 images or 10,000 images or 100,000 images, how does learning curve look like? So in ICML 21, they had some analysis based on that. So what we have done is that we have introduced a calibrated version of it, which I think, in my opinion, is pretty important. So these learning curves are in general evaluations of self-supervised learning frameworks, or any transfer learning framework is missing two important baselines. One of them is blind guess, and the other one is gold standard, and also on top of that, scratch. So these are really important because, first of all, any data set comes with some basic biases. So let's say if you're looking at surface normals, it's a very interesting one. I was not expecting it the first time I was looking at this image. If you average all the surface normal images in an indoor data set, you'll end up with something like this. This kind of shows that, well, there's a ceiling, of course, on top, there's a floor on the bottom, and there's many of the images show kind of a corner-ish thing, right? It makes sense. Now, what is the performance of this thing? This is an important point because it's a blind guess. It means that any learning method that you do that works based on the specific instance should outperform this. But it is surprising that some of the self-supervised learning methods actually do not even outperform this guy. Yeah, which means that, you know, this baseline was generally missing. And there's more than that. For instance, the scratch, if you have a transfer learning based framework, let's say if you say that I have 10,000 images and I pre-train on this self-supervised learning method and then transfer to another task image set and so on using 1,000 images, it's important to put that in perspective with respect to what you would get out of if you train only on this 1,000 images. That's basically the scratch baseline, right? So the calibrated learning curve framework that we have, it brings all these like multiple baselines into perspective and calibrates the learning curve using a standard way. So everything goes into perspective. Let's say, look at this curve, for instance. But first of all, gold standard also, it means it's an approximation of the best result that you get using your architecture. Let's say if you had almost infinite amount of data using your architecture, what would be the best result to get? Of course, we don't have infinite amount of data, but for many of the data sets, we have millions of images, so we can approximate it. So the idea of calibrated learning curve is that when you get a learning curve, you calibrate it with respect to a stretch between 0 to 1 between gold standard blind guess.
I mean,
and then you also have
quickly checking that we are like 2 minutes over the time, but I mean, you can take like maybe 2 or 3 minutes to wrap up, or yeah. So
yeah, sure. Yeah. I can stop just right here. I'm just going to finish just explaining this curve, and then we can move on. And this is the scratch curve, which is the performance of if you didn't do, let's say, if this is using method 1, self-supervised method 1, and this is using the scratch curve. I can turn this into kind of a PR-ish style, like calibrated risk versus a scratch calibrated risk. And you want to be in below this triangle in general, because that's what it basically means by how much you outperform the scratch. So this is work in submission. Hopefully you'll see it soon. But I wanted to say that this is a useful way to characterize tasks, because that tells you the learning speed of different tasks. And this is, for example, useful for curriculum learning. If you want to design a curriculum of learning multiple tasks on one data set, if you don't want to learn them all simultaneously, which you would think that learning them in cascade would be useful because some of them provide foundation for others, what should exactly govern this cascade? What should govern this curriculum? You would think that learning speed is one of the aspects of it, because if you learn something fast and it's foundational for others, you can learn it first and then learn the more complex tasks coming up. And this is the characterization of it that I wanted to mention. So, but I don't have time to get into it, but I give you the sneak peek of it is that even on one data set using the same images and so on, different tasks at different learning speeds. For instance, this is the learning speed of steps, and this is the learning speed of surface normals. You can see the surface normal learns faster. What is the consequence of this? I guess that's a discussion for another talk. I'm going to stop here, I think. And I didn't get into discuss some of these questions, but yeah.
Thank you very much. I mean, it was a very excellent talk. Yes, I think that we can actually ask maybe 2 questions. Or I mean, just to remind you, Amir will also be in the panel discussion. So if you have some more general question about the multitask learning in general, we can also have opportunity to talk to him in the panel discussion. But now I think we have time to maybe to have 2 more questions, especially some of that has been listed here on this slide. So yeah, go ahead. So any question from the audience? Or? Yes, so are there any questions? I mean, that Amir just presented quite a bunch of very exciting topics, from data set collection to how we actually, you know, I mean, relate to multiple tasks. That if you have multiple tasks, basically how to learn them together, what would be the consistency relationship between them. So
I guess Saturdays are not the time for asking questions.
If no one else has, I can ask one.
Yeah, go ahead. Go ahead.
Thank you for the excellent talk. So I would ask, in the Crosstask Consistency work you presented, I guess it makes sense why the improvement comes. There's this relational expression of the tasks, right? And you enforce consistency. Why do you think in Omnidata, and from what I saw, Omnidata kind of outperforms Crosstask Consistency, right? So correct. Why do you think this comes from? Is it like better data? Is it that simple, or is it something more complicated, you would say?
Yeah, because I think they're doing different things. Why would Crosstask Consistency actually be able to let you generalize to unseen camera parameters? There's no concrete reason for that to happen. So they're doing different things. I don't think they would replace each other. Like, yeah, I mean, at some point you have some architecture in which there is some inductive bias that can internally handle, say, a change of camera parameters or like change of field of view and so on. Then yeah, you would expect it to be able to emerge through learning, but that's just simply not the case. So it's, to answer a question, we have to know that what our architectures can do, how much we can squeeze out based on consistency across different frames, like think about from a like information theory perspective. And camera parameters are just not some of those. And that's why I think.
Okay. But you're saying you're already trying to put cross-task consistency on top of Omnidata, right? Yes. Okay.
Yes.
That
I mean,
that would be an
there's
interesting
signal
result.
to believe that. Yeah, there's signal to believe that that's useful because we are looking at Omnidata and generally MIDAS, let's say, experiments. And actually, MIDAS doesn't come with surface normals, but this one we can extract surface normals out of it. And they're on Omnidata, they're not coming out to be consistent, even though they look better and even though they're more robust, which again suggests that these are kind of orthogonal axes.
Okay, thank you very much.
Okay, yeah, thank you very much again, like to Amir for the excellent talk. So